Hello everyone, today I'm going to introduce a new type of foundation models called large concept models. It is proposed by FAIR at MetaAI. Hopefully this will be a game-changing idea for foundation models. Okay, so the intuition here is that large foundation models have certain limitations. They operate at the token level and lack higher level abstraction. That means their limitations include being language dependent, so they need to be fine-tuned on the text of each language, and the knowledge they acquire differs based on the corpora they are trained on. And they are also modality dependent, so when you input content into the foundation models, reasoning layers, it depends on the specific modality. But large concept models operate, or let's say reason at a concept level. The way they achieve this is by encoding sentences from any language or any modality into the concepts using a model called SONAR. So the concept model don't have to worry about language or modality. That means they decouple the modality and the language encoding from the reasoning. Here is the workflow. The concept encoder that is part of SONAR takes the input, that is words in any language, any modality, and outputs the concept embeddings. And they are fed into the large concept models. And the output of the large concept models is then passed to the decoder layer of SONAR so that it can be decoded into a specific modality and language. So here is a workflow in detail. The input to SONAR is sentences. So we need to split the original text or audio into sentences. Then the SONAR encodes a sentence into an embedding space. And the large concept model autoregressively predicts the next concept embedding from the previous concept, similar to the large language models, but it is operated at concept level. And afterwards, the output of the large concept models is fed into the SONAR's decoder, which then decodes the next concept into a sentence in your chosen modality and language. So SONAR is a language agnostic and modality-free sentence embedding model. Its training strategy is as follows. It is an encoder-decoder model, and it uses a teacher-student approach to train for the speech modality. That means a pre-existing sentence embedding space, which is text-based, acts as the teacher and guiding the training of a student encoder for the new modality speech and align those embeddings to the teacher's embedding space. So the SONAR model is trained on 200 languages for text and 37 languages for speech. The way it works is that it processes inputs at the character level to avoid tokenization, and it uses a universal embedding space for multilingual sentences. With cross-lingual training, aligning similar embedding across different languages. And the modality-free property is achieved in the way I mentioned. Speech encoder is trained to align speech embeddings with text embeddings through teacher-student learning. Okay, then let's come back to the large concept models themselves. So the concept representations are used in reasoning to predict sentence embeddings rather than token embeddings. They autoregressively predict higher level concept embeddings. The higher level here means higher than tokens. And there are three variants. So one is base LCM, which trains the objective with mean squared error loss on embeddings, and similar to a regression task. And there is the diffusion-based LCM inspired by latent variable models, and there are quantized LCMs, which use vector quantization for efficiency and reasoning. So the base LCM architecture is a transformer model. So the main difference from the regular transformer is that it doesn't have an embedding layer that converts tokens into vectors, and it doesn't have the top layer that converts the predicted vector into the probability of a token. And it's trained with MSE loss. This is a very straightforward model designed with decent baseline performance in zero-shot tasks. The diffusion-based LCM is inspired by generative diffusion models, and it can model complex embedding as noisy latent variables. The benefit of using this kind of training method is that it increases the mutual information between the embeddings through the diffusion process and excel at paraphrasing and generating diverse concepts. And the key idea is that it predicts the original concept embedding x0 through a diffusion process. It starts from a random embedding, and that is pretty much just noise. And at each diffusion step, it uses a transformer to take the previous concept embedding as input and predict x0 hat, and that is the next concept embedding without noise. And through multiple denoising steps like that, it gradually refines it towards the target embedding x0. Yeah, so this is a typical diffusion-based method, and there are multiple variants. So, for example, another common one is to predict noise, but in this paper they picked to predict x0. And the next type of large concept models is quantized LCM, which is based on residual vector quantization for embedding efficiency. And the process is that concept embeddings are mapped with codebooks of quantized vectors. So each concept vector is converted into a series of tokens that correspond to the codebooks. They model residuals with the codebooks to iteratively refine representations with multiple codebook lookups. And the LCM transformer predicts the next tokens corresponding to the next concept, conditioning on previous concept tokens, and construct the embedding of the new concept with these tokens. Then about experiments, they use multiple metrics and multiple data sets. So in all, diffusion LCMs outperform quantized LCMs, and then the worst performant models are the base LCMs. I won't get deep into it, so you can read the paper about that. And then I want to talk about the limitations of the model. The major limitation I find with the current large concept models mainly arise from defining a concept only at the sentence level. This may not be appropriate for all scenarios. Some sentences are more complex, and they have multiple clauses, and some are simple. And the process of sentence segmentation itself can be error-prone. Another limitation is that human reasoning often integrates multiple layers of abstraction simultaneously. So the human brain can dynamically alternate between top-down, that is the high-level planning inferential details, or bottom-up, like details influencing high-level understanding reasoning. So the LCMs are restricted to single concept inference. So it lacks this flexibility to reconcile different levels of abstractions. Yeah, that's all. Thank you for watching.